Lipids are biological compounds that dissolve in nonpolar solvents such as chloroform and diethyl ether. They may be fats or oils, terpenoids, waxes, or steroids, for example. Most long-chain carboxylic acids of biological origin are found as esters of glycerol. These esters could be oils if they are from plants, or fats if they are of animal origin. Usually, oils and fats are triacylglycerols or triglycerides. Oils are generally liquids at room temperature. Fats are solids. The hydrolysis of triacylglycerols yield fatty acids. Fatty acids are long-chain carboxylic acids. Most natural fatty acids have unbranched chains with even number of carbon atoms. They differ in length, degree of unsaturation, and position of the double bond. Saturated fatty acids have higher melting points than unsaturated fatty acids. This is because of the molecular shape of these saturated fatty acids, wherein they can be stacked quite easily in the presence of another. Unsaturated fatty acids lead to kinks and difficulty in stacking. Because of this, their London forces are not as effective as in saturated fatty acids. As a result, their melting points are lower. Natural unsaturated fatty acids have cis double bonds that are usually not conjugated. Triacylglycerols with higher content of saturated fatty acids have higher melting points. Fats have higher content of saturated fatty acids, and so they are solids at room temperature. Plant oils are liquids at room temperature because of the presence of unsaturated fatty acids. The IUPAC numbering of fatty acids follow that of carboxylic acids. The carboxyl group is at C1, followed by the regular numbering pattern. Common nomenclature uses the Greek letters alpha for carbon right next to the carboxyl group, followed by beta, gamma, and others. The farthest carbon from the carboxyl is called omega. Fatty acids can be identified by shorthand notation, and this notation takes the form C:D, where C is the number of carbons and D is the number of double bonds. For linoleic acid, there are 2 double bonds and there are 18 carbons in this molecule, so the shorthand notation can be 18:2. The position of the double bond is indicated by either a delta followed by Mn superscript or simply Mn, where M and N indicate the carbon number from C1. Here, the double bond is at position 9 and position 10. We just indicate 9. And another double bond is at position 12. Take note that these double bonds are not conjugated. There is an sp3 carbon between them. Hence, we can identify the double bond in this way, delta 912. Another way is to write them directly inside a parenthesis. The double bond can also be identified by the omega system, where X is the carbon number counting from the CH3 tail end. So if we count from the tail end, 1, 2, 3, 4, 5, 6. This double bond is omega-6. Linoleic acid is an omega-6 fatty acid. Here is a list of common fatty acids that are found in nature, including their shorthand notations. Acylglycerols can be monoacylglycerol with just one fatty acid attached to the glycerol unit. Take note that glycerol itself is not chiral, but when a fatty acid is positioned at one of its terminal oxygen atoms, it becomes a chiral molecule. The central carbon is a chirality center. Since this fatty acid is derived from myristic acid containing 14 carbon atoms, this compound is called 1-myristyl glycerol. The attachment can be at the terminal oxygen or at the internal oxygen, in the case for 2-palmityl glycerol. Palmitic acid has 16 carbon atoms. We also have diacylglycerol or diglycerides, where two fatty acids are attached at different positions of the glycerol unit. In certain cases, diacylglycerol may be chiral. Triacylglycerol is when there are three fatty acids attached to the glycerol unit. The fatty acids may all be identical, such as here for tristearine or 1,2,3 tristearylglycerol. Stearic acid contains 18 carbons. Triglyceride can also have different types of fatty acids, such as in this case. The ester groups of fats and oils may be hydrolyzed under acid or base catalysis. A typical reaction is called saponification, for example by using sodium hydroxide. This yields salts of carboxylic acids and glycerol. The salts of fatty acids can be called soap in general. The polar end of a soap molecule is hydrophilic, while the nonpolar end is hydrophobic. A soap micelle places the hydrophilic head, that part where the carboxyl group is present, in contact with water, and the center contains the hydrophobic tails, which can be used to isolate grime in this case. Transesterification can also be done with fats and oils. For example, when you mix methanol with triglycerides in the presence of an acid or a base, methanol can displace glycerol to form esters of carboxylic acids. Hydrogenation of oils yield cooking fats. For example, margarine. This double bond becomes reduced in the presence of hydrogen with nickel catalyst. Partial hydrogenation isomerizes some of the cis double bonds to trans double bonds. This often has a detrimental effect because trans fats have been associated with an increased incidence of cardiovascular diseases.